You know you have the lowest grade distribution for like A's out of like all the 241 teachers?
Really? That's not a good sign, is it?
Nope, not at all.
I was looking at that. I don't know.
Well, we are rolling. We are at lecture 50. Interesting fact, though, that's something I would pay attention to if I were in your seat or I were in your shoes. One of those distributions I can explain. Last spring, it was a very unique class I had in 141.
I think that's what I looked at.
Yeah.
It was like 5% A's.
Yeah, I can explain that, but I won't explain it while the cameras are rolling because I might hurt somebody's feelings. We are going to start substitution today. We will not finish substitution today. This is a technique of integration that we will use throughout the rest of this course, and you will use early and often in Math 241. So it is something you want to make sure that when we're done with it, as far as working with it over the next 3 or 4 days of class, that you have a good handle on. Because, pretty typical in this class, things advance, and what we're learning today kind of moves into the background of another problem, and you're expected to do substitution, but that's not the real goal of the next problem. It's something else beyond that, but you have to know it in order to do the problem. Pretty typical of things in this class. So what we're going to do is we're going to take a pretty ugly looking integrand, and we're going to make a substitution, or sometimes called a change of variable, and we're going to try to make it look easier. I used to say that we would make it an easier problem, but if you really think about that, you can't make a problem easier than itself. It's still the same problem. So we're just going to try to make it easier looking to do the problem. Now, I could write some things down, and I'll write a couple things down, and they are not going to help you at all until we look at several examples that relate to that. And then you say, oh, that's what that U thing was, and that's what that DU thing was. Here's an example that I'm going to go ahead and write a couple of these down. And this is the section that begins substitution. Or change of variable. So we're going to take a complicated looking, and honestly, when we get beyond this and you've done this for a couple weeks, you don't have to write everything down that we're going to write down. You can say in your head, well, I'm going to let U represent 3x. Do I have the derivative of U? I don't. I'm going to correct for it. And you kind of think through it, but we're going to actually write it down. Here's an example of what we now have at our disposal and what it's going to look like in this particular section. That's a pretty easy problem. Antiderivative of e to the x, anti-differentiated with respect to x. What do we get for the integral of e to the x dx? That's e to the x. Okay, and we know that. We know that if you differentiate that result, you're right back to the integrand. If you take the derivative of this, you're right back here. The dx really is a dummy variable that tells us to anti-differentiate with respect to x. So in substitution, it's going to look like this. Doesn't that look the same? Everywhere there was an x, there's now a u, right? And in fact, that's kind of the goal of substitution, is to mirror that simpler version. Well, it's not never going to be e to the x dx, but it can be e to the u du, where u is representing some function of x. So I'll be somewhat generic with this. So here's what it really is. It's really e to the f of x, and then you have the f prime of x present in the integrand. And if it bothers you that there's not a d something, there's actually then a dx there. So that becomes the du. And instead of just e to the x, we have e to some function of x. I happen to like this one better because it it's a whole lot like our simpler rule, so I'll probably use that more, but this is what it really looks like. And one other kind of basic rule that we have is, I don't know, there's a bunch of basic rules, including the trig, but let's just say this one. 1 over x dx. What is the antiderivative of 1 over x dx? Natural log, absolute value of x. It's kind of a chain rule component or matching term with respect to substitution. That's probably overly simplified, 1 over u du. If it looks like that, what would you think the answer would be? Natural log absolute value of u plus c. Now, u is kind of disguised. Again, u is some f of x that we choose before we attack the problem, and we think that'll make it look simpler. But you're going to have 1 over that function. That's our u thing. And then we're also going to have the derivative of that thing present in the integrand. But I think it's probably clearer and simpler in the form of 1 over u du. So we're going to change an x problem that's integrated with respect to x to a u problem. And in order to integrate a u problem, you have to integrate it with respect to u. That's not very helpful. I know that. Okay? The most helpful thing is to look at examples that fit into this particular type and examples that fit into this particular type, and then you say, oh, okay, yeah, I see that's really a simpler problem once we make the substitution. All right, so let's do some examples. Hopefully during class today and certainly in class tomorrow and over the next couple days, you can begin to take over more and more of the kind of intelligent guessing responsibility of what we choose to let you represent, because that's what you have to do on your own. Now, I've chosen the first few examples. Specifically, this one I chose because we can do this problem two ways. We can do this problem because we have this function of x to a power instead of just x to a power. Up until this point in time, we've had x squared and x to the fourth and x to the negative second. We've had just x raised to powers. Now we've got some function of x that's raised to a power. So since we're starting substitution, let's let u equal x plus 4. It's the function that's being raised to the power, since we're switching horses here and we don't just have x raised to a power. So we've made this choice for u. Hopefully it's going to make it look a little simpler. This isn't that complicated of a problem anyway. But with this choice for u, what's the derivative of this u thing with respect to x?
1.
Would be 1. And then if I multiplied it, I know du over dx is a separate entity, but I'm going to treat it as differential of u over differential of x, so I can multiply both sides by dx. So if I multiply both sides by dx, I get that. That's also kind of something new, is that this thing that's really one thing, du over dx is really one thing, but we're treating it as two separate things, numerator and denominator. So there's our original substitution. In order to change an x problem integrated with respect to x to a u problem, we've got to be able to integrate it with respect to u. So with these two things, our problem becomes what? Instead of x plus 4 squared, it's now u squared. That looks better. And I need, in order to have du in the integrand, we've got to have 1 dx. Do we have 1 dx? Okay, so here's u squared, and dx is the same thing as 1 dx, so there's our du. So without any corrections, compensations for changes that we made, that's why I chose this as the first example. X plus 4, the quantity squared, integrated with respect to x, becomes simpler, I think. Is that a little simpler looking? Yeah. It is to me. U squared du, well, what do you think would be a method that we could integrate u squared integrated with respect to u?
The antiderivative.
The antiderivative, and what rule would we use? I guess it would be a better question. Add 1 to the power, divide by the new power, right? So if we were integrating this, we would expect to get u cubed over 3. Now that's not exactly the power rule the way we learned it. What was it the way we learned it? Wasn't it x to the n dx, right? We had just x to a power. Now we've got, I know it doesn't look like it. It looks like just another letter, but isn't that a function of x? U is x plus 4, which is technically a function of x, not just x itself. So if it's x to the n dx, we knew that was x to the n plus 1 over n plus 1. Now it's not x to the n, it's u to the n, same rule, u to the n plus 1 over n plus 1. It's a general antiderivative or an indefinite integral, so we've got to include the plus c. End of the problem?
No.
Okay, why are we not at the end of the problem? We integrated. Okay, we didn't start with a u problem. We started with an x problem, right? We had x's in the original problem. We better have x's in the final answer. We changed it just to make it a little simpler looking so we could integrate it, and then we're back to the original substitution. So wherever there was a u, we want to replace it with what u represented temporarily. Any question on that substitution problem?
So you don't take the antiderivative of the inner function?
Well, we kind of did. The inner function is x plus 4. All we had to do is make sure that we had its derivative present in the integrand. So that if we didn't have that, if we didn't have du here, we couldn't do this problem. Listen.
How did you know that du over dx is 1?
Because we made this choice for u, and we just took the derivative of both sides. Well, we've got u in terms of x, so we have to derive u with respect to x, since it's in terms of x. So derivative of u is really, I mean, if you ask yourself the question the right way, what is the derivative of u with respect to x? It's derivative of u with respect to x. And then this side is in terms of x. What's derivative of x with respect to x? 1. And what's derivative of 4 with respect to x would be 0. This is the step we're going to kind of forego. Eventually, we'll do that on the first 2 or 3 problems, and then eventually we'll go directly to this step. What is du? It's 1 dx.
Is it ever something like 2dx? Or?
Yes. Yeah. I'm starting real simple here. And sometimes we don't have this. We lucked out in this problem, and I wanted that to happen in the first example. We had 1 dx in the integrand. So we had basically the equivalent of du. So we didn't have to do any corrections. Now, I chose this problem because we can do this problem another way. And I want to compare and contrast because the answers are slightly different, and see if you think their answers are equivalent. So we'll come back to this sheet. Let's do this same problem. Before we had substitution, we could still do this problem. How could we do it? Square it. So that's x squared plus 8x plus 16 Now we don't have a function of x to a power. We just have x's, and things are added. So we can integrate them or anti-differentiate them separately. What's the antiderivative of x squared?
X cubed over 3.
Antiderivative of 8x.
4x squared.
Okay, 4x squared, or I'll just write 8x squared over 2. That's what it becomes eventually. Antiderivative of 16. 16x, and then we'll have a plus c. Now, those answers don't look the same. So there's our answer this way. The substitution way, we integrated this, and we got x plus 4 cubed over 3 plus c. So let's see if they're close. Let's cube this. X plus 4 cubed. And we're not going to do that on every problem. We're just trying to compare and contrast our answers here. What's the first term of x plus 4 cubed? X cubed. The next coefficients are 1, 3, 3, 1, right? So it'd be a 3. X would be squared. And this thing would be to the first. Is that right? Next coefficient is 3. X would be to the first. 4 would be squared. And then the last term has a coefficient of 1. X to the 0, 4 to the third, right? So in our answer, that gets divided by 3. X plus 4 cubed divided by 3. Well, x cubed over 3. Is that in the other answer? Okay. Here we've got a 3 over 3 that's going to reduce. So the next term would be 4x squared. Is that in the other answer? It is. 3x times 4 squared, which is 16, divided by 3. The 3's knock out, and you're left with 16x. That's looking good so far. Now it kind of falls apart because we've got 4 cubed over 3, which is 64 thirds. Does that appear in the other answer?
That's your constant.
Okay. I'm going to make these constants different, which they are potentially different. So the terms that have to be there, the things involving x cubed over 3, it's in both answers. 4x squared, both answers. 16x, both answers. There's some arbitrary constant added on here. Is all this constant? So if they differ, remember this is an indefinite integral, we've got the possibility of some unknown constant at the end. Apparently this constant, C1, is different from this constant, C2. In fact, we know in this particular example, they differ by 64 thirds, right? But if you differ in an indefinite integral, you better only differ by a constant, because that's the only thing that's still kind of unknown when you finish the problem. So this answer, without using the substitution principle, and this answer where we did use the substitution principle, they are the same answer. They differ by a constant. All right, next problem. You know, whoever chose that word, that's not a very good word, because doesn't it indicate that we're going to have some difficulty? I mean, it's a problem. Here's a math problem. It's going to be a problem, right? It's going to be an issue. How about an opportunity? Here's our next opportunity. We'll give it a new name. See if it catches on. It won't.
There he is.
We're going to make a substitution. We're going to get rid of some ugly term. Kent has already made a recommendation for that ugly term. There's really only one ugly term, and that's the term that's under the radical. And you'll know very quickly when you do a substitution problem, you'll know within a few seconds when you get to the next step and you find du, was that a good choice? Is that going to help the cause? So Kent said we're going to let u equal 8x plus 5.
Why wouldn't you make it equal to the square root of?
Okay. Excellent question. Is it the square root that's causing a problem, or the fact that we have something ugly under the square root that's causing a problem? Could you do this problem if it were the square root of x and you wanted to anti-differentiate that? Yeah, the stuff under the radical is pretty darn simple. But it's not the square root that's causing a problem. It's the fact that we have some function of x under the square root. But that's a good question. And there is an occasion where we will want to let u be the whole thing. But for the most part, especially when we're first getting started, if we can change this so it's the square root of u, that's a plus. We have made some progress. We're kind of in this area when we've made it the square root of u. Good question. So that's our choice for u. What's the derivative of this u thing with respect to x? 8. And again, that's the step I'm going to omit here, but not yet. So du is 8 dx. Now we've got to do some kind of sliding things around here. This is the easy part, because that's why we made the choice we made here for 8x plus 5. That's going to become what? The square root of u? Now, it's everything else that we can mess with numerically. It's got to be numbers. Can't do anything. We can't change any letters. We can't change any x's or square root of x's or add any letters, but we can correct for numbers. This 5, I'm not really liking where that 5 is. If we don't like it and it's multiplied by the radical, what can we do with that 5? We could bring it outside. Same problem. We haven't done anything except kind of factor that out in front. We need an 8 dx in order to change this problem to a u du. We've got to have du if we're going to integrate the new version. Dx is there. The 8 is not there. Is this legal? Can I multiply by 8 as long as I divide by 8? I know that looks pretty stupid. Certainly you can do that, right? Everybody agree? 8 times 1/8 is just 1. You can multiply anything you want to by 1 and you're not going to change it. I don't want the 1/8. I just had to do that to get the 8. So the 1/8, I'm going to slide it out in front. So I slid the 5 that was already there out in front. I manufactured the 8 myself. I can't just manufacture 8. I'd like to take all the money in my wallet and multiply it by 8. Okay? I can't do that. I'd have to also divide it by 8 to equal the amount that's in my wallet, which isn't very much. And I know that seems a little awkward to multiply by 8 and then divide by 8, but there's a purpose for it, maybe not unlike anything else we've done in here. Now that we have an 8 and a dx, what is 8 times dx? That's du, and that's the purpose. So here's du. What is this guy? That's the square root of u. And then we're stuck with some baggage out in front, but that happens in a lot of these problems. So is the integrand easier looking than the integrand that we started with? I think it is. And it's not that much different, but it is different. It's easier. U to the square root of u is u to the 1/2. And as long as we've got a du there, we don't want u's and x's, okay? So if you've got u's and x's in the same integrand, that's an issue that we've got to resolve before we anti-differentiate. But we've got u and we've got du, so we're in business. What's the integral of u to the 1/2 du? U to the 3/2 over 3/2 plus c. So we got it into a form where it looked easier. We integrated it. Now it's a matter of kind of reconciling the numbers and resubstituting. We made it look simpler so we could integrate it. Now we're done integrating, we substitute back. So wherever there's a u, we replace that u with 8x plus 5. So we've got a 5/8. We've got division by 3/2, which is multiplication by 2/3. We've got u to the 3/2 plus c. And earlier in the problem, we made a substitution. We replaced 8x plus 5 with u. So now we're going to undo that substitution. Where there's a u, we'll replace it with 8x plus 5. Now that's kind of way overkill on this problem. But it's the first problem of this type. Any questions or issues with that, Jonathan?
Back on the first page, when you multiplied 8dx by 1/8, could you just solve that du?
Yes. Some of you may have done this that have had some calculus before, and I'm not going to do the problems this way, but it is legal. You maybe will take this equation and say, well, I want to see what dx is equal to, and you'll solve for dx, and dx is what? du over 8. And you'll put in du over 8 for this dx. So you'll get your du, and then you've also got a little extra baggage of an 8 in the denominator. What will you do with that? You'll bring it out in front. So the net result is the same. So if you're used to doing that, you keep right on doing that, but you probably won't see me doing that in the examples that I do. It is valid. To tell you the truth, I can't remember which way your authors show in the textbook, but they're both valid methods.
I think it's the same way you do it.
They kind of
I
put numbers there in correct form out front. They're both good. Anything else before that gets set aside? I'm not seeing those looks like I can't believe that I'm going to actually do this. So that's a good sign. Third example. That's kind of a mess. Now, if the dx, I'm sorry, I got too many dx's. The dx is already in the numerator. If that bothers you that it's just dx, then put a 1 up there because that's certainly valid. Dx is 1 times dx. So there's the thing that we want to make look a little bit easier. And these are guesses, but we want to try to make it an intelligent guess. What choice might we make for you that might make it look a little bit easier? Okay. Now, with that choice, where are you headed with that choice? Natural log. Okay? We're hoping to make this integrand, and this is kind of what's in the back of your mind as you make these decisions. I'm hoping to change this into an integrand that looks something like this. 1 over some variable quantity, and that's okay as long as I have the derivative of that variable quantity. So that's kind of the goal, or the goal, right? So I'm going to skip that next step where I find du over dx and just basically go to du. What's the derivative of u? Negative 3 dx. So here's our original problem. So for 1 over 5 minus 3x, I'm going to call that what? 1 over u. We have a dx. There's what we need to have. We need to have a negative 3 times dx. All we have is the dx. What can we do to the integrand, and how could we compensate for what we did? Multiply by negative 3. and then also multiply by negative 1/3. That's correct. So negative 3 times dx, that's what we need to have du. We didn't have all that present, so we had to kind of manufacture this factor of negative 3. So in doing so, we now are kind of strapped with a little baggage out in front. Is this an easier problem than easier looking problem than what we started with? You make that choice. I think personally that it's easier looking. Just drag that little baggage around. It's part of the answer now. What's the integral of 1 over u du? So we got it looking simpler so we could integrate it. We now integrated it. We now change back to the original variable. Everywhere we see a u, we replace it with 5 minus 3x. Now, it might be the case that several of you in here, especially if you've had some practice in the past, high school class with integral calculus, you can look at this original problem and go directly from this original problem to this answer. I would wager there's probably 3 or 4 of you in here that kind of do this in your head already, and you can go from here to here. All of you will be able to do that in this problem in your head in a couple of days. Question before we move to another one? All right, got to have some trig. But as trig integrands go, this is a pretty simple one. Now, if this were the cosine of u integrated with respect to u, we would like it a lot better. What would that answer be? What has cosine for its derivative? Just be sine, right? Well, unfortunately, we don't have the cosine of some letter and then the derivative of that same letter. So if this is where we're headed, then the obvious substitution is let u equal 3x. Derivative of u is 3 dx. So there's cosine of u. And back to Casey's question, it wasn't the cosine that was a problem. It was the fact that we didn't have just x here. That's the problem. We had the cosine of 3x. So we don't want to let u equal the cosine of 3x, just the 3x. So that's cosine of u. Is that du? Can we make it du? What do we have to do to correct? Okay, to get du, we need a 3 and a dx. We have the dx. We need to multiply by 3. I can do that if it's a number. I can't change anything that requires any variables. I mean, just a simple reason. Why can I not multiply by x and divide by x? Well, what if x were 0? I'd be dividing by 0. So I can't multiply by things and divide by things when they have variables in them. There's a lot of other reasons why we can't do that, but that's enough. So now that we have 3 dx, and we multiplied by 3, so we have to also divide by 3. So this is now du. So aren't we right here now? Cosine of u, du with a little extra baggage out in front. What's the final answer?
1/3 sine 3x.
Sine of, actually, let's do this first, so you're a step ahead of me. So we replace u with 3x. And anytime you doubt an answer, don't you have a built-in check?
Take the derivative.
Take the derivative. So if you take the derivative of this, sorry, plus c, what should it be? It should be the original integrand before we started doctoring things up, right? So it should be cosine 3x. if that's true, and I think you can probably do that one in your head, right? You see why the 1/3 has to be there? Because if you were to differentiate sine of 3x, you'd get cosine of 3x, but what else would you get? You'd get a 3. There wasn't a 3 in this original problem, so we better kind of have something present that's going to take care of that multiplication by 3. That's the purpose that the 1/3 is solving.
Dr. Riggs,
Yes?
will we ever be able to do like x squared? Like at the top where it's like cosine 3 of x. When x to a higher power, it's going to be du equals 3
Yeah, okay. Let's actually do that before we do our next example. That's a pretty good question at this point in time. Let's suppose that the original problem is the cosine of 4x squared. I think that's what your question is, isn't it?
Yeah.
Okay, when this has an x squared, we're not going to be able to do this problem this way. And here's why. Because if we were to start by letting u equal 4x squared, here's where it falls apart. What's the derivative of u?
8x.
8x dx. Well, the dx is there. We could create our own 8, but the x is not there, and we can't create it, so this method is going to fail. Now, that's not to say that we can't do this problem some other way later on, but substitution is not going to solve this problem for us.
Okay.
You could let u equal 4x, though, right? And then have u cosine of u squared.
Remember that you can't separate any of that. I can't take one of those x's and bring it out because I don't have just that x. I have the cosine of that whole quantity. So all of that, there's no way, other way we could try this problem other than to let this whole thing be u. Can't take any of those aside. Now, when I first started writing some example problems down, this was actually my first example problem. And then I thought of several other things that we probably should do before we look at this one. This is very typical of a substitution problem. Kind of, the other ones we looked at were kind of overly simplified. This is a little more normal substitution problem. The integrands can get pretty ugly looking, and then you see things in the integrand like the x squared, and you say, well, what is that there for?
Can you multiply it through?
You could.
I'll
I'll let you prepare this and come up next class and do it. I want you to raise this to the 7th power and then distribute x squared to everything. Okay? Not really. That'd be mean.
u equal 2x cubed plus 1.
But there is a purpose for the x squared. What's the purpose?
The derivative of 2x cubed plus 1 is 2.
It has an x squared in
X
it.
squared.
Yes. So this is what I said earlier on another example. You're going to know pretty quickly if your choice for u, like we just did that problem that Blair suggested, we knew within 30 seconds after choosing let u equal 4x squared that it wasn't going to work. So if you let u equal this ugly quantity that's being raised to the 7th, derivative of u is
6x squared.
6x squared dx. Now you say, are we going to be able to accommodate that x squared that's in the integrand? Yeah, in fact, it has to be there. This x squared has to be there in order for us to do this problem this way. You've got to have an x squared. We do. You've got to have a dx. We do. Now, eventually, we've got to have a 6. But if the 6 isn't there, we can manufacture the 6 as long as we compensate for it. So the 6 is not there. Let's multiply by 6. Multiply by 1/6. Now we're in business. So all this circled quantity is really what? That's really du. We needed it all. And we changed this problem to a u problem, so we've got to have a du in the integrand. And then what is this piece right here? U to the 7th?
Yep.
So here's what we have. We're stuck with this 1/6 out in front. This ugly function of x to the 7th is now simpler looking. It's just u to the 7th. And everything else in the integrand, the 6, the x squared, and the dx are all needed because they are all parts of du. That is clearly simpler looking than what we started with, right? What's the integral of u to the 7th du?
U to the 8th divided by
U to the 8th over 8.
plus D plus.
So the work is done. The substitution made it look easier. We were able to integrate it. Now we go back to the original letters. So we've got 1 over 6 times 8, 48. U to the 8th is really 2x cubed plus 1 to the 8th. Again, your check is take the derivative of that. You'd be back to the original integrand. Questions on that one? I think the value of the substitution, as we do more and more examples, will get more and more clear why we're doing the problem this way. In a week, you'll be doing this problem in your head. You'll do all this part right here in your head. You'll say, okay, I need a 6x squared. I've got the x squared. Multiply by 6. I can't do that without also dividing by 6. And you basically go right down to either this version or this version. You don't believe me, I can tell by looking at the way you're looking at me. All right, I want you to do more of this one on your own by making... This is very similar. Looks different because of the radical, but it's the ugly function under the radical that's what we're dealing with. Okay, the choice Jonathan made is 7 minus 6x squared. You like that?
Yep.
Does it have a chance of working?
Yes.
Why?
Because you have the extra.
Okay, because the derivative of this thing is going to have an x in it, and don't we have an extra x floating around in the integrand?
Yeah.
Okay, so it has a good chance of working. du is?
Negative 12x.
Yeah.
If you don't like the x where it is,
No.
that's the square root, so I'm just going to call that to the 1/2. And then this x that's here, I'm just going to move it down to the right, just because that's where I want to deal with it anyway. What next?
You have to make the negative 12.
Okay, we need that. We have it. If we didn't have that, this method will not solve this problem. So this method would fail. dx is there. It's going to be there. We need a negative 12. So multiply by negative 12, multiply by negative 1/12. What is that stuff that's underlined there? That's du. So what's the integrand now?
U to the 1/2 du.
Everybody agree? Easier looking?
Yep.
I think it is. What's the integral of u to the 1/2 integrated with respect to u?
U to the 3/2 divided plus C.
So negative 1/12. Division by 3/2 is multiplication by 2/3. U to the 3/2, and wherever we see a u, we're going to replace it with
7 minus 6x squared.
end of problem.
Yep.
That's the same really as the previous example. The previous example was something cubed. This is something to the 1/2, but other than that, they're pretty much the same. Questions before we move that one? All right, got lots of good examples here. Trying to decide. This is about 3 or 4 steps up the ladder of difficulty. Probably not the greatest choice on my part, but let's see if we can make this a simpler looking integrand. Do you know of any integrand that looks at all like this one that would be simpler if we can convert this one into that form?
Isn't sine squared plus cosine squared 1?
Okay, that's true. Sine squared plus cosine squared is 1. Is this integrand? Let me do this.
It's the inverse of
Ooh, yes.
something. Tangent? Sine? One of them?
One of those inverse deals, right? One of those inverse trig deals. So there was a sign up here. I'm going to multiply it by 1, and I'm actually going to move the sign out here to the side. And I did that so that this might look familiar. 1 over 1 plus something squared, which is what Catherine said. 1 over 1 plus x squared. dx is one of those inverse trig functions. Inverse tangent. So that's kind of where we're headed with this problem. So if that's where we're headed, then we want this to be, normally we'd want it to be x squared, where we're not going to be able to be that simple. So it's going to have to be u squared. So if that's going to be our u squared, that pretty much makes our choice for u, right? If u squared is going to be cosine squared, then we better let u equal cosine. Is that okay with everybody?
Yep.
Now, I don't know if it's going to work, but I do know it has a chance of working, and I'll know when I write this line down if I think it's going to work. What's the derivative of cosine of x?
Sine of x.
Sine of x dx.
Sine of x?
Negative.
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 Sine of x dx. Is this going to work?
Yes. Yeah.
It's going to work. Because I don't care about the negative. I can correct for signs of numbers. But I've got to have a sign, and we do. And we've got to have a dx, and we do. So let's rewrite the problem. It's 1 over 1 plus, well, it's cosine squared. That's really for us now, that's u squared. And is all this out here at the right, is that du?
Yes.
Kind of.
You have to
We need a negative 1, so we'll multiply by negative 1 and divide by negative 1. Or if you want to say multiply by negative 1 twice, that still works. So now that the negative 1 is here, negative 1 times sine of x times dx, that's all du. Now, we're strapped with this out in front. No big deal. Just don't forget it. Is that a simpler looking integrand? That's way simpler.
Well, now it's tangent inverse as well, right?
Yes. Now it's exactly inverse tangent. That's what this is. Inverse tangent of u. And this is easy to finish this problem. Wherever there's a u, we want to replace it with cosine. That looks kind of bad. That answer looks bad. But we're done now, so we don't care how bad the answer looks. We wanted it in this stage so we could integrate it. Then we'll substitute back, and it can look as ugly as it needs to look when we're done. Now, I intentionally did not do a problem today that had limits of integration. But let me do one thing before we stop. Let's say we were doing this problem right here. What are these? Aren't those x values?
Yes.
How do you know they're x values? Because we're integrating with respect to x. So we're going to have to pay attention when we change this to a u problem. Those aren't going to work anymore because those are x values. So we can either change the limits or wait till we get it back in terms of x and reinstitute the x values. But I intentionally stayed away from those today, and we'll start with those tomorrow. Have a good day.